In this clip, a vision system labels a man in a dinosaur costume as a truck with high confidence. The key issue is not the wrong class, it is that the model behaves as if it is still in its training world. It outputs a confident label when it should output I don't know or reject. This is exactly what auto-distribution detection is about, detecting inputs that don't belong to the training distribution. Today's question is AOD detection learnable? Not does it work on a benchmark, but can we learn a reliable reject rule from finite training data under clearly stated assumptions? First, let's take a look at some definitions. In-distribution means that inputs are generated by the same process as the training set, the training world distributions. Out-of-distribution means that inputs are generated by a different process. This is outside the training world. AOD detection is an open set decision. We do not need to classify the dinosaur. We only need a binary decision. Accept, this looks like the training world, or reject, this looks outside. And the reason deep nets fail here is well known. They can assign high confidence to inputs they have never seen. To detect AOD, most practical detectors have the same form. You compute a scalar score, S of x, you compare to a threshold, and with my convention today, higher score means more AOD. So if S is superior to the threshold, then you reject, otherwise you accept. A key rigor point, the deployed detector is not just the score. It is the score plus the protocol used to choose the threshold. That will matter when we talk about learnability and generalization. Now for the common metrics. AUROC measures ranking quality. It's the probability that a random AOD gets a higher AOD score than a random ID. And false positive rate at 95%. True positive rates means that you choose a threshold so that you detect 95% of AOD, or accept 95% of ID depending on convention. Then measure the remaining error rates on the other side. What's important is that AUROC can be good while a single threshold still fails after deployment, because AUROC ignores the calibration protocol. Now, learnability. We assume deployment data are a mixture of two sources. With probability of 1 minus p, we get an ID sample from the training world, and with a probability of pi, we get an AOD sample from the outside world. The learner only gets ID training samples and must output a detector. PSE learning, meaning probably approximately correct learning, means that there exists an algorithm that, from a finite number of training world samples, produces a detector whose error approaches the best possible error as the sample size grows, uniformly over a specified family of possible test worlds. Fang called that family the domain space, the set of shifts you claim to handle. So AOD detection is only learnable relative to a declared domain space. And we're gonna see that sometimes you cannot learn at all. First negative result, if you allow any possible AOD world, AOD detection is not learnable. The reason is identifiability. You can build two different test worlds that produce the same training world observations, but require opposite accept-reject decisions on some inputs. If the training data cannot distinguish those worlds, no algorithm can guarantee small error on both. So, distribution-free AOD detection is impossible in general. You might propose a strong assumption. ID and AOD supports are disjoint. They never share the same inputs. That helps, but it still doesn't solve the problem. Outside the training world is an open space, with finite training sample. You cannot characterize all of it. Without additional structure, you still cannot guarantee a low-risk rejector. So what makes it learnable? Learnability becomes possible when you restrict the allowed test to words, and the hypothesis class is compatible with that restriction. Fang give learnability results for restricted domain spaces. Think controlled families of training distributions or structural assumptions, where a near-optimal detector exists uniformly across the family. In other words, you must state what shift you target. Then, choose a model score training to match those invariants. Let's go from theory to practice. Choosing a score is not neutral. Softmax confidence, Odin, energy, they each encode a hypothesis like OD will cause lower confidence or OD will have higher energy. That is exactly a restriction of the domain space. If deployment OD violates the hypothesis, failure is not surprising. It is consistent with the theory. So let's start to explore those scores. And let's start with output-based method. They use the network outputs to produce an OD score. The simplest baseline is maximum softmax probability, often called MSP. The MSP takes the model's predicted probabilities and keep the largest one. If that max probability is low, we suspect OD. Now look at the first plot. It shows the distribution of MSP for ID versus OD on a real setting like a Cypher-10 classifier tested against SVHM. The important observation is the large overlap between the two distributions. This overlap is exactly the practical expression of a known phenomenon. Neural networks can be overconfident on OD inputs. If MSP is not separable, thresholding is intrinsically hard. Now the energy-based framework aims to replace confidence with a score that is often better aligned with typicality. You take the log sum and exponential of the logits and multiply by -t. In many plots, we flip the sign and show negative energy because ID typically has lower energy, so negative energy is higher for ID, making the axis consistent with higher equal more ID-like. And the second plot shows exactly that compared to MSP, the energy-based score often yields less overlap between ID and OOD. That makes thresholding more stable. Lastly, Odin. Odin is an inference time method designed as a safeguard against that overconfidence. It modifies MSP using two tricks. There is a temperature scaling, which divide logit by a temperature T before softmax, and small input perturbation that slightly modify the input in the direction that increases the predicted class probability. In other words, Odin tries to make the network's confidence behave differently on ID versus OD at test time, without retraining. Odin's score is still essentially a max softmax score, but applied after temperature scaling and perturbation. All in all, but none of them promise any OOD. They assume a shift family. So here comes the training time method. If the theory says learnability requires restricting the domain space, one practical way is to inject training time information about outside. Outlier exposure does this. You train with auxiliary outlier data and add a term that encourages high uncertainty on those outliers. In other words, you feed the training task, but don't be confident on these outside examples. But the threshold selection is part of the problem. Many papers silently tune the threshold on one particular OOD validation set. And that embeds a hidden assumption. Your calibration OOD represents deployment OOD. If deployment OOD changes family, a fixed threshold can fail even when AURC looks good. So we must always report the calibration protocol, the data used to pick the threshold and the target operating point. The demo will do two things. First, reproduce standard OOD evaluation, train a Cypher-10 classifier, compute MSP, Odin energy scores, and evaluate AURC plus FPR 95% TPR on multiple OOD datasets like SVHN and textures.
So, is OOD detection learnable?
Well, not in the unrestricted total space. There is an impossibility. It becomes learnable only when the domain space is restricted and a compatibility condition holds, meaning the detector class contains an hypothesis that can jointly serve ID accuracy and OOD rejection across the entire space. In the dinosaur clip, the root cause isn't the dinosaur. It's that the system never defined and never validated a trustworthy reject option under the shift it will actually face.